Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like, can that robot forge metal? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week we're exploring how robotics and artificial intelligence are transforming metalworking. From manufacturing replacement parts for the military to crafting bespoke car parts, faster and more efficiently than ever. Before we get started, don't forget to check out the Robot Talk shop at robottalk.org/shop, where you can get your hands on some awesome Robot Talk merch. Share your love for robotics with the world with one of the Robot Talk t-shirts, stickers, or mugs. So, with all that said, let's get on with this week's interview. I recently had a great discussion with Edward Mehr from Machina Labs about their RoboCraftsman that shapes complex metal parts for the aerospace, defense, and automotive industries. Today, I'm speaking to Edward Mehr, co-founder and CEO of Machina Labs, a company using AI and robotics to manufacture complex metal structures. Hi Ed, welcome to Robot Talk.
Thanks for having me. Excited to be here.
So you co-founded Machina Labs in 2019 with the aim of developing intelligent, adaptive, software-driven metal factories. So to get us started, can you tell us a little bit more about what Machina Labs does?
Yeah. So, if you want to start from the problem, the big problem we have in manufacturing is that factories are custom built, right? So for any physical product that you see out there, there's a lot of specific hardware and machinery that needs to be developed for that factory to work, right? So factories basically take a lot of time, a lot of money, and they're very custom and specific to that design, to that material you're trying to manufacture. The moment you want to change that design, you want to change to a new material, you have to change the factory. And that's why things take forever, right? In automotive, the design cycle for building a car is now five years for fast companies.
Yeah.
In aerospace, we're looking at, 7 to 10 years, right? Because you have to go build the factory. So this is non-existent, for example, in the software world, right? You can build something and then immediately distribute it. That gap from design to implementation and distribution is pretty short. So what we're trying to do at Machina Labs, build the next generation of factories that resolves this issue, right? A factory that can, in the morning, make, airplane parts, in the afternoon switch to car parts. Make it intelligent and flexible enough that can easily switch from one design to another, one material to another, and completely get rid of this problem. And this is going to unlock a future where, designs can easily become products, 3D products, right? So significantly increases the speed of development, the speed of manufacturing, speed of innovation in the hardware space. So that's the problem we're solving at Machina Labs. Can we build factories that are more similar to data centers? They can have different products being built in them just through a change in the software, as opposed to changing the hardware of the factory.
Yeah, that's really cool. I know very little about the manufacturing world, but one thing that kind of has permeated into the public consciousness is this idea of economies of scale and how you need to be manufacturing an awful lot of the same product for it to be worthwhile. But it sounds like, if you don't have to invest all this time and money into building a massive factory for your specific product, does that kind of go away?
Yeah. I think it's kind of funny. A lot of people talk about economies of scale as it's a rule of nature. Yeah. It's a law of the universe. It's actually a technological problem. What economies of scale means is that I need to invest in something before it gets to a certain scale. And then a certain scale, that the amount of things that comes out of that investment, the value that it creates, it starts paying off for that investment. But if you have a system that can easily switch to another product without change in investment, you don't have to invest in that system further to create a new product, to create a new hardware product, then there is no economies of scale, right? Like only variable cost exists. There's obviously certain investment you need to do to build that flexible system, but that flexible system has the ability to do all kinds of products where every new product, you don't have a fixed cost. So economies of scale goes away.
So let's talk about the flexible system. Your flagship robot is called the RoboCraftsman. So can you describe this robot for the listeners and explain what makes it special?
Yeah. So it's a RoboCraftsman because it's designed to basically operate like a craftsman. It doesn't look like a humanoid, but it is, in all intents and purposes, it's supposed to operate like a human, but with much higher force, much higher precision to do manufacturing processes, right? So it can pick up a drill and do drilling if needed, but then drop the drill, pick up a welder, do welding if needed, drop that, pick up, in our case, our first and most flagship process, sheet forming, and almost shape a sheet of metal, shape into a metal like a craftsman, a sheet shaper would hammer it into shape without the need for any tooling, any mold, or any dies. The system operates like a craftsman, hence called the RoboCraftsman. It can work with different types of material. It can autonomously pick up different tools. It has a tool tray that it can choose from to do what it needs to do, and go from like feedstock all the way to the final product without any geometry-specific, material-specific tooling. The whole system is also in a container, actually, right? So it's actually two 20-foot containers, ISO-compliant containers that open up like a transformer and any warehouse floor, as long as you have flat, concrete floor, and you have power, you connect it to the power and it's ready to go. It self-calibrates itself and it starts, you put a feedstock, a sheet of material, a metal in it, and then it can pick up the right tool and start going through the operations to make the part within the same day, actually, of arrival in a new location.
Okay. So for the format of an audio podcast, to me, it looks like a big kind of industrial robot arm, the kind of thing I'm used to imagining in a car factory.
Yeah, no. So the robot themselves look like a segmented robotic industrial arm, but they're integrated in a platform that, like I said, it's portable in a container. It has different set tools that it can pick up, different control systems that are versus a traditional factory where a robot does the same thing over and over again. We have different computers and control systems that look at the sensor data and are adjusting what the robot does in every 4 milliseconds. So it's an online active control loop. Mm-hmm. There is a software that comes with it that allows you to prepare, your geometries, your parts for production, and then analyze the final results. For example, the robot, after it forms it, it scans it and it gives you, what it did. So you can look at that data and do analysis, do QC. The system also uses that data to build models to improve what it does, right? So over time, as it does more and more, it also learns from the result that it achieved and constantly improves or potentially learns new operation. Mm-hmm. Yeah, so the robot themselves look like segmented robotic arms, but there's so much else going on around it, from the platform, from the tooling, from the sensors, and the fact that they are reactive to the environment, right? They're constantly looking at sensors and based on that, deciding what they need to do next.
Yeah. In some of the media coverage of your company, I've seen the description robot blacksmith. How close do you think that analogy is?
Yeah, no, it is pretty close, right? So you think about what a blacksmith does. A blacksmith takes a feedstock of material, heats it up a little bit, and then it starts hammering it and give it a shape. Mm-hmm. We're almost doing the same thing, except we started from sheet metal. So we start from a sheet of metal, two robots coming in. They have these end effectors that look like a ballpoint pen, but like a very strong ballpoint pen that can deform steel and aluminum. And they're basically slowly shaping that sheet into a complex structure. We're now adding heat to the system as well. That's one of the R&D projects we're working on right now. So they can actually do thicker sheets, so even get closer to what forging and craftsman blacksmith operation looks like. But yeah, it's a very, very apt analogy. We're scaling basically what a blacksmith does with robotics and advanced software. Mm-hmm.
I've watched a couple of videos of the system, and it quite often it shows two robots on either side of a sheet of metal kind of working in unison. Can you talk a little bit about that?
Yeah. So, going back to that analogy of a craftsman, you need almost your two hands to work the material, right? For the sheet forming process, yes, there's two robots on two sides. almost, the best analogy is when you think about pottery, right? So, how you come in and pinch a clay bowl as it's like spinning on a pottery wheel and you give it shape. These robots are also starting from a flat sheet. They come from two sides, start pinching and deforming the sheet into shape. So you need both robots for a forming process. But for example, if you're doing trimming, you only use one robot. So if you're doing scanning, you're only using one robot. You're on version 2 of the system that has 2 robots. Version 3 might have more.
Okay.
It might have 3 or 4 robots, right? So as we are supporting new operations beyond sheet forming, for example, if we want to do assembly, if we want to do welding, we might need even more degrees of freedom to be able to position parts in the correct way and do subsequent operations. But yes, today the version 2 of the system has 2 robots.
Okay. Yeah, that makes sense. So as you mentioned, you're primarily working with sheet metal. What are the main challenges of that as a material and how do you address those?
Yeah. Sheet metal is an interesting material. It's actually the largest of a format for metals, and actually also pretty cost effective. A giant 10-foot by 5-foot sheet of metal, a common alloy is like $200-$300, right? So very accessible. Compared that, for example, to a 3D printing, that same amount of metal in powder is thousands of dollars, right? So very cost-effective feedstock for metals. It's also very versatile because most of the metal parts that you build are usually enclosures. They're containing something else, right? Like for example, you're a car, you're an airplane. You have the enclosure. You have a container of where you put other things in it, right? That's what makes sheet metal very versatile for a lot of different applications. But at the same time, because it's sheet of metal, it's very flimsy. It's very hard sometimes to work with, as opposed to, for example, you think about machining, you have a block of material. It's very stiff. You can have a mill come in and, chip away from it and give it a shape. With sheet metal, when you start deforming it, it moves in all kinds of unpredictable ways because it's thin material. It's almost like a more stiff version of a cloth, right? So it's actually pretty hard to work with it. And that's why up to now, making a mold, a die, and then applying a pressure in a stamping press or a hydraulic press was the only way to give metal shape, like using a mold. With us, for the first time, using advanced software, using modeling, using robotics, we can basically come up with this non-intuitive way to work with this material and account for all these unpredictable ways that it moves and do a very non-intuitive set of movements and process parameters to get to a final part. The same way human looks at a sheet of metal, maybe hammers a little bit and then adjusts and then hammers again to give it a shape. For the first time, because modeling algorithms and artificial intelligence is getting to a place where we can use them in these types of settings, we can process this material. Otherwise, it's very finicky to do that, to deal with it, unless you have a very rigid die that stamps it into shape. So it makes it hard to work with. But then the flip side of that is it's a very versatile material. It's basically used everywhere. You're looking at $280 billion market for sheet metal parts, right?
Wow.
Everything you see, you're sitting in a car in a freeway, you're in a sea of sheet metal parts.
Yeah.
Like every car next to you is a sheet metal container. You're sitting in an aircraft, you're in a sheet metal tube. A lot of rockets are basically sheet metal tubes. The fuel tanks are sheet metal. So it's everywhere, but it's a little bit of a finicky material to work with.
Yeah, it's one of those things that you don't give much thought to, but now you're listing these, I'm like, yeah, it is everywhere, isn't it? So we had a related question from Montgomery on Twitter, and it's a little bit of a technical question. So please, try and answer it in a way that everyone can understand. So the question is, how are you handling sim-to-real transfer in material springback, force control, and variability? Any breakthroughs using digital twins or physics-informed machine learning to bridge the gap from simulation to physical metal?
Yeah. No, this actually goes at the crux of the previous question, right? So if the material is very finicky, basically the moment you start applying force to it, you're trying to manipulate it, it moves in unpredictable ways. Actually, you have a very hard time coming up. What is the right set of process parameters the robot needs to go through to turn it into a good shape, into an accurate shape? That was the biggest problem we had to solve, right? So there are 2 ways to do that, right? You can say, hey, in order for me to come up with the right set of process parameters, I need to have very good simulation of this process because doing trials in the physical world is very expensive. I need to be able to simulate how I can deform the sheet of metal with a robot. and then explore what type of process parameters I need to come up, how the robot needs to move to get to a right accurate part, because, it's a very finicky material to deal with.
Yeah.
The problem with that has been up to today is the simulations are both very computationally expensive, right?
Mm-hmm.
Especially if you're simulating physical process of deformation of a sheet, spring back that person mentioned. These are very expensive processes to simulate. So it takes a long time to simulate, our process in virtual world in computers up to now, right? So, a process that maybe a robot can form in 2-3 hours, it will take weeks to simulate, traditionally in a computer. So that was one problem with the simulation. Then the other problem is it is not that accurate, right? The simulation is a proxy of the reality, so it's not that accurate. And that's what this person mentioned. What is the sim to real gap? What is the difference between simulation and reality? So when we started the company, we decided to actually not go down the simulation route.
Okay.
We tried to go down the route of first, try to make it easy to run real experiments, to actually form metal in real world with the robots and capture data. So as opposed to thinking about the simulation, to capture data in real world of the process forming and manipulating the material. So we started with that. We wanted to make that process as easy as possible, as cheap as possible to capture real data. That was the start of our process. We captured a lot of data. Now we are actually also augmenting that with simulation, where we're developing our own simulation package. We're using latest advancement in GPU to make fast simulations, right? So that's one way we're solving the speed problem. But the way we're making simulation also accurate is that now we have this trove, a wealth of data that we have generated, and we're constantly generating on shop floor from real physical data. So simulation gives us some results, but there is some gap between that simulation to reality. That's usually called residuals. And then we try to find those those errors, and try to model those using real data from actual physical trials that we have done in the shop floor. So now we have very accurate sims, right? We use physical calculations and physical equations to get 80% there. And the last 20%, we use actual physical trials and the data from real world to make the sim very accurate. Now we can do trials. Once we have that, we can do trials in the virtual world as well. And it's much cheaper than doing trials in the physical world to come up with the right set of process parameters to form an accurate part.
Mm-hmm. Okay.
Does that make sense?
That does make sense. Thank you. So, I guess that's part of what you mentioned earlier about learning as they go, as each robot forms a new part, it learns and gets better. Are there other aspects where there's learning going on in the process?
Yeah, no. So the core operation is like learning how to deal with the material, but also you can start learning about when those your robots are potentially getting damaged, right? Like start looking for signatures of damage, starting to look at signature that your robots are out of calibration. You start looking at learning when the sheet metal, maybe the sheet of material that you received maybe is defective and it's not actually meeting the specification. So there's a lot of stuff around the process that you can figure out. But, this is very interesting because, a lot of people in the world of AI up to today have only relied on the data that exists on the internet to build these, chatbots, chat GPTs of the world, right? But we're running out of data, right? So in order for us to have more intelligent systems, we need to figure out new ways of interacting with the universe, with the world, and generate new data. And this is what these robots are doing. They're actually basically, running massive science experiments on scale, but dressed as manufacturing. There's outcome of product that comes out. You can buy a car door, which is these robots are manufacturing. But every 4 milliseconds, they're running a science experiment. They're applying force and physics to the material and then capturing what's happening, right? So now for the first time with these systems at massive scale, we are capturing a way of interacting with the physical world and capturing data. So this hopefully opens up ways to understand, for the artificial intelligence to start understanding physical phenomenons beyond just user-generated content on the internet.
Yeah. And I guess this comes back to that analogy of the blacksmith who would learn through years and years and years of working with the material, how it responds and the kind of that intuitive understanding of the physics. Obviously, the blacksmith doesn't necessarily have the kind of scientific understanding of it, but they understand intuitively how to operate with the material. It's
kind of interesting. I think, you mentioned that I used to work in a sheet shaping shop to make, classic cars like 1930s Fords, hot rods. And we worked with this master sheet shaper. His name is Bobby Walden. We were all apprentice. He was training us. And we were basically hammering and forming sheets into shape to make these, hot rods, these, classic cars. And he had such a great understanding of material science, of how sheet works. And this person, never went to college, but very deep understanding. And I had a friend of mine who was a material scientist in there, and it was everything he says is true, but he's using a completely different language than what we're using, right? And to your point, it's basically empirically through experience, this person has intuited how the material works. And basically it's equivalent model to material science models, but in different terms and in his own language of that he gave to it.
Yeah, exactly. So you've mentioned a bunch of different areas that kind of shaped sheet metal is used. What would you say is your main kind of client at the moment?
Yeah. So by the way, sheet metal is our core operation. Since then, we have moved on beyond it. Right? We are basically teaching RoboCraftsman to do all kinds of metal operations, right? Sheet metal was the first one. We have now since moved on to trimming. So we can do trimming, slotting, hole making. We do QC. So the robot actually can scan the parts that it makes. We're looking at heat treatment, welding, assembly. Those are the few operations we're going at. So the idea is that a system can go from just a feedstock material all the way to the final assembly, not just a sheet metal formed part. The main benefit we provide today is that flexibility, right? And flexibility, what it means is kind of the brother of speed, right? If you're flexible, your factory can easily switch to one thing to another. That means you can make a new product really fast. So if you can make a new product really fast, the industries that have that need for agility and speed are become your main customers. So when we started, defense was very natural fit, right? Our first customer was NASA, but then the second customer was Air Force, right? And since then, we have done a lot of work in the defense space. For example, if you look at what is actually happening in battlefield, there's a lot of weapon systems that are sometimes 50, 60 years old that are being used. These are not high volume weapon systems. There's only 50, 100, 200, a few thousand of each, right? But they've existed for a long time. When these things get damaged, there's not a factory that's constantly producing parts for these things. So they need to have an agile, fast way to repair parts, create new parts that make sure the system stays online and doesn't have to go down. So that ended up becoming our first customer, right? Can we make repair components? In the defense world, they call it sustainment of weapon systems. Can you make repair components much faster than traditionally possible? And to give you a perspective, a landing gear door or a panel on a legacy military aircraft goes down, sometimes it takes 4 years before they can replace it because there's no factory making these things, right? So what they end up doing a lot of times is either there's a plane in the junkyard that they can go get these parts off of and then get these planes up and running, or they need to go find a manufacturer, design the tooling, the machinery for it, manufacture it, and then replace the part. And that's a 4-year life cycle. And sometimes, you're looking at spending $1 million on a single plane panel to be replaced. So we're turning that 4-year lead time, 4-year timeline into sometimes 2-3 days, right? So 50, 60 times faster than traditionally possible. That was the first area. And then since then, we've moved on to also new systems, right? If you're making, 200 or 2,000 of the same missile, and then at that point, you're going to switch to another version, building a giant $200, $300 million factory makes that missile very expensive, right? So those are the areas that also we're working with defense primes to significantly give them acceleration they need to manufacture these products and come up with new designs. More recently, we also have found our way into automotive, but this is not a traditional automotive. For example, recently we announced a partnership with Toyota where for the first time using our technology, people can build custom cars at mass producible prices. So you can go buy a Toyota Tacoma or a Toyota Tundra, but your Tacoma, your Tundra doesn't need to look like everybody else's Tundra and Tacoma. And this is a pretty big deal because cars are one of the most expressive products we have. It's expensive, but it's very expressive. People really tie that to their identity. A person who drives a clean car really cares about environment and wants to express that through that purchase, right? But there's really no way to customize and make these cars individualized up to today, especially on the exterior. But we're enabling that with Toyota. So for the first time, you can go buy a Tacoma that the tailgate of it is a design that you would like. Maybe it's your favorite sports team, or it's something about where you live. You can design the hood to be also your own design, your doors to be your own design. So completely new category in automotive. We have also seen a lot of interesting demand on heavy equipment, agricultural machinery, where, again, the volumes are lower and the mix is high. There's a lot of changes in design and material that happens on lower volumes. But yeah, I think to your initial point, sheet metal is a large industry, so there's a lot that we can do.
Yeah. Yeah, it's really interesting, varied work. Before you co-founded Machina Labs, you worked at Relativity Space, a company building rockets for long-term space exploration. And there you helped develop the world's largest metal 3D printer. So can you tell us about this 3D printer and why this technological breakthrough was transformational for the industry?
Yeah. So at Relativity, we wanted to solve this problem, the same problem we're solving almost at Machina, but with a very specific angle on launch vehicles and using 3D printing. Before at Relativity, I was at SpaceX. And one of the biggest challenges that I saw at SpaceX was that, it actually takes a very long time to turn designs into products, even at a company like a SpaceX that's super agile, maybe at the forefront of manufacturing, right? You look at the timeline for SpaceX. Right now, people think of SpaceX sometimes as a startup. It's not a startup, right? Like it started in 2001, 2002, now it's 2026. It's like 25 years of this company. And there's basically just two rocket families, right? We have the Falcon family that is very mature product and generates a lot of cash for the company. And then there's a Starship family that's still in test and development, right? It hasn't made his, first, productionized flight. And both of these rockets have been manufactured in two different factories, two different even actually states, because the initial point we talked about, factories are very custom built for the product you're trying to make. So you need to almost build the factory before you build the product. Elon famously says, like, factory is the actual product, right? Because once you have the factory, then you can build the product. So I saw that and I was kind of pretty disappointed. I was like, why can't things take much faster? Like, what is the blocker so that we don't have to wait 25 years to make two versions of a rocket? Peter Thiel famously said in the 60s, we were promised flying cars. And then in 2025, we have 144 characters. So we just got Twitters and Instagrams, right?
Yeah.
So what happened? And the real reason for that is just the speed of innovation is very slow in the hardware space because of, limitations of manufacturing. So when I joined the early team at Relativity, the goal was, hey, can we make rockets, but can we make them fast? And can we make them not only fast, but also in a way that we can also make them on Mars? And when we go into, other planets, it's easy to make components for it. And we were like, okay, the way to do it at the time is 3D printing, right? If you 3D print the components of the vehicle, you can go from software instruction, from a design to a final product very easily. So we built this very large 3D printer, and that was my team, where, basically very similar to what it looks like at Machina Labs, these giant robots with a 3D printing head and building, structural components of the vehicle, the body of the vehicle, 30 foot tall, 10, 15 foot diameter articles, like a fuel tank for a rocket. And that company's doing great. Recently, I think it's being run by Eric Schmidt, which is the ex-president of Google. And I think they're working toward, their first flight, their first commercial flight. They actually did their first flight a few years ago. But what I realized when I was there was 3D printing is part of the solution to this flexible manufacturing, but not the complete solution, right? And that's what, kind of prompted me to start Machina, to look at a platform that can use this 3D printing when it's needed, but then it can use our forming process when it's needed, pick up forming end effector, forming tools, and do forming, and pick up trimming tools when it's needed and do trimming, what we call hybrid manufacturing, right? Pick the right tool and do the right process for the right part. But one big thing that was a interesting theme at Relativity, and we still have it here at Machina as well, is that also at some point manufacturing needs to happen in space, right? Once we start colonizing Moon and Mars, we need to be able to also manufacture that, build the things that we need there. And none of our factories are portable today. Right? You cannot move a 4-story stamping press that makes panels for a rocket easily into space, right? So we need to start thinking about systems that are also portable. So that was also forefront of our mind. And that's why we made RoboCraftsman portable. So it's not only portable on Earth, but tomorrow you can put it on a fairing of Starship and send it to space and make manufacturing possible on Mars as well.
Amazing. Yeah. Well, I hope to one day see one of your robots on Mars.
Yeah, me too.
Ed, it's been great talking to you today. I've been chatting to Edward Mehr from Machina Labs. Thanks, Ed.
Thank you.
Thanks for listening. If you enjoy Robot Talk, please share the podcast, subscribe, and leave a review. And check out @Robot Talk Pod on social media to see a photo of Machina Labs RoboCraftsman in action. Next week, I'll be speaking to Alison Okamura from Stanford University about collaborative haptic systems. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.